All right, we're about to start a new subject. If I can get all this stuff off the board or off the window. Okay, so hopefully you guys can see this right now. I just started recording the video. We're going to be studying linear algebra. I'll be following this book by Sheldon Axler, Linear Algebra Done Right, which is a very excellent book, goes into the theory, does a lot of simpler examples as well, and also gets into inner product spaces, which hopefully I'll be able to talk about eventually, which is important for quantum mechanics and physics, especially vector spaces over the complex numbers. So maybe we'll get to this eventually. I just wanted to show you the book. Here is the website for it, linear.axler.net, and he just published a fourth edition. Okay, let me close that. Okay. All right, so that is the textbook we'll be following, and oops. So it's called Linear Algebra Done Right by Sheldon Axler. This will be lesson 11. We'll probably follow this for a month or so, a few weeks. But yeah, so I think linear algebra is a good topic to go to after calculus, differential calculus. Maybe way later I'll show how these subjects can kind of be combined. So you have manifolds and calculus on one side, and then you have tangent spaces, which are vector spaces, on another, and you can sort of look at the tangent bundle of a vector, and that tells you a lot of information about the algebraic topology that's going on. So yeah, a very nice subject, linear algebra. The theory works out very nicely. There's certain theorems, like every vector space has a uniquely defined dimension. If it's well, it could be finite or infinite. But yeah, we'll get to that. So let's try to motivate the subject a little bit. So like, why would you want to study linear algebra if you never have before? Or if you're already taking it in a class or something, then you're motivated by your class, right? But let me give some motivation, like how you might arise at this subject. If you're kind of coming up with it yourself, right? So what we study is these linear equations, and we want to find solutions to them. And linear equations show up, throughout math and economics and chemistry all the time. So let's go into lesson 11. I'll just say linear algebra done right. With examples. Okay, and really broad based, what do we study in linear algebra? We study something called vector spaces. So the usual vector spaces we study they're going to be n-dimensional vector spaces over some field. Usually the field is the real numbers or the complex numbers, which hopefully you're familiar with. Real numbers is like your usual number line where there's no holes. Complex numbers is this like two-dimensional number, quote-unquote line, but it becomes a plane. So usually our vector spaces will be some sort of Rn, which is n Cartesian products of R. This is just a list of n things that are numbers, that are real numbers. So you could have like 1, 2, 3.5 pi. That would be something in R4. Or you could do the complexified version where you have n complex numbers. So you could have like 1 plus I, comma, 1 minus I, comma, 2 minus I. That would be a list of 3 complex numbers. That would be something in C3. And it seems like we're gonna give an abstract definition of a vector space later, but it actually turns out that every vector space where the field is real numbers or every vector space where the field is complex numbers is one of these two for some integer n, positive integer n. So even though we can define this sort of abstract notion, we always come back to these two vector spaces most of the time anyways, once we fix a basis. And so these are really our main two vector spaces of study. We could also go over a finite field. It could be a finite field to the n power as well, but I don't think we'll talk about this as much. This might show up more in like number theory, and there's some good combinatorial results and some sort of number theory results when the field is finite. But usually we'll just be dealing with real numbers, complex numbers, and complex numbers more for mathematical physics, quantum mechanics, stuff like that. Or actually, really, it won't be CN for quantum mechanics. A lot of the times you have these infinite dimensional function spaces or operator spaces that don't commute, and you have operators on some large function space that's infinite dimensional, so it usually won't be finite dimensional like CN, but it will be a complex vector space. So if you're interested in physics, of course, I do tutoring in all of this math, so if you're a physics student as well and you want tutoring, we have the email address mathpondofficial@gmail.com. You can shoot me an email and we could schedule something over Zoom. But yeah, so these are our usual vector spaces, and now let's try to motivate. So how might you arise at this notion of these vector spaces, sort of like, without knowing the definition of a vector space, or what's the core fundamental problem that we're trying to solve. And like I said before, this is just, we want to solve linear equations. So we have some set of linear equations. It might be, it might just be one equation. It might be more than one equation. And we want to solve them all simultaneously for all the values. So let me give you a quick example of that. Oh, yeah, 1 second, I need to grab something to erase the board. Okay. Okay, so we're studying these abstract vector spaces, and the motivation is we want to solve these systems of linear equations. So let's do an example. And also, let me just point out that Axler doesn't really approach the subject this way. He kind of expects that you've seen this already, so I thought I would go over in the introduction a little bit more motivation, actually going through the systems of linear equations that would lead you to studying linear algebra in the first place. So he kind of skips over this a little bit. He expects you know this, but I'm going to do a simple example, and hopefully that will illuminate things a little bit. So here, let's write down the equation first, and then we'll give it some motivation too. So let's say we're looking to solve 2x1 plus 3x2 is equal to 8, and we want to find two values x1 and x2 that simultaneously solve the first equation and also satisfy that 10x1 plus 1 times x2 is equal to 12. So essentially, linear algebra systems of equations, what you want to do is you're trying to find two values, x1 and x2, which you could think of as a vector in R2, two real numbers, or they could be complex numbers, but let's just stick to real for now. Oh wait, good morning. I just saw your chat. Linear algebra start the new year. Yes. Yes, it was just published. Yeah, I saw that too. Yeah, very good book though. Yeah, highly recommended. So, linear algebra, right? We're trying to motivate it. We have this linear equation. We're trying to solve it for x1 and x2, which you could think of as a list of two numbers or an element of R2. It's a two-dimensional vector. And we want to find these two numbers that not only satisfies 2x1 plus 3x2 equals 8, but it has to also satisfy the second equation as well at the same time. So we can't pick one solution for the first equation and then try to pick a different equation for the second formula. We want it to simultaneously satisfy both of them. And so maybe we want to give this a word, some sort of word problem to motivate it. It could be chemistry, but I think the easiest is probably just economics, something to do with money. So let's assume that we have two items in a store and they cost different amounts. So x1 costs some amount, which we don't know, and x2, the second item, costs x2, and we don't know what that amount is. Let's say it's like lollipops and, I forget what I put, lollipops and Kit Kats. And so person one, let's say they bought 2 lollipops and 3 Kit Kats, and we know that they spent $8 total. Right, so person one buys 2 lollipops and buys 3 Kit Kats. And let's say person 2 buys 10 lollipops and also buys only 1 Kit Kat. Okay, and then let's assume, so the lollipops cost x1 dollars and the Kit Kats cost x2. And let's say person one spent $8 total. So that's person one's total spend, and person two spent $12 total. Okay, so just a little bit of like a real world motivation. So we're really just trying to solve this linear equation, but that's equivalent to trying to solve this word problem. So we basically want to know how much do the lollipops cost and how much do the Kit Kats cost per individual item. And we know that the first person bought 2 of the lollipops and 3 of the Kit Kats, and they spent $8. So we're really trying to figure out, okay, how much could the lollipop cost and how much could the Kit Kat cost, such that when I buy 2 of the first and 3 of the second, I spend $8. There's a lot of solutions here, right? If we don't have the second equation to help us, there's actually infinitely many solutions. I could solve here for x1 and it would be a function of x2. So if we're just given one equation with 2 variables, here in this case we actually get infinitely many solutions. We don't have enough information essentially to figure out how much this x1 cost and how much this x2 cost. But once we introduce another equation, that sort of lowers the dimension in one sense. So here we had a one-dimensional set of solutions, and here we sort of intersected it with this other one-dimensional set of solutions, and we got a zero-dimensional set of solutions, which is just a point. So here there's something called, you can write this into a matrix and go to reduced echelon form, and there's this whole process we'll probably talk about eventually, but I just want to solve this kind of more basic, just kind of, solve it by hand. How would you solve this without knowing any linear algebra? It's pretty easy. There's only 2 variables, 2 equations, right? And we'll check our answer at the end, right? So maybe I'll leave up this equation, but this is the main word problem. So person one's buying this set of things. They spent $8. Person two spent $12. They bought 10 of the first, 1 of the second. And now let's try to figure out how much each thing cost. Okay, so basically there's a couple rules of things we're allowed to do to these equations. So without changing the answer, meaning that the set of solutions doesn't change if I multiply both sides of the first equation by like 5, for example, right? Because if this is equal to this, then 5 times this has to be equal to 5 times the thing on the right. So as long as I multiply by some invertible number, meaning like not 0, then I can always undo that result, and the set of solutions shouldn't change as long as I do something that's invertible. So basically, I can add things to both sides, I can subtract things from both sides, and I can multiply or divide by some non-zero number on both sides. And I shouldn't change the solution. So instead of looking at this set of equations, it might be easier to look at when I take the first equation and multiply it by 5 on both sides, and that's because the x1 terms will line up, and then when I subtract the equations from each other, we'll be left with an equation with only one variable, and then we can just solve it the normal way. One equation, one variable, you just solve. It's a linear equation always, so if it's one variable, it's pretty easy to solve. So let's multiply the first equation, left and right. So this part is the left side of the equation, this would be the right side of the equation, and we're just going to multiply by 5 so that the 2 and the 10 here match up, because 2 times 5 is 10. All right, so I'm going to get a similar set of equations. It's going to be 10x1 plus 15x2 is equal to 40, and 10x1 plus 1x2 is still equal to 12. Okay, and now you can see, since this is equal to 40 and this is equal to 12, well, I can just subtract sort of like the sides from each other, if that makes sense, because this is equal to this. So if I subtract this from here, it's the same thing as subtracting 12 from 40, since they're equal to each other. So if I do that subtraction here, right, 10x1 minus 10x1 is 0. So I just get 0x1. 15x2 minus 1x2 is 14x2. And 40 minus 12 is 28. So I started out with two equations, two variables. I basically made the first coefficient for one of the variables, or the first variable in this case, equal to each other. They were both equal to 10. And then I subtract the equations from each other to eliminate one of the variables. Now I have an equation that's just 14x2 equal to 28. And of course now I can just solve that easily. Right, that implies that x2 is equal to 2. And if x2, remember that once you solve for one variable, then you can plug it into either one of your equations, it doesn't matter, and you can solve for the other variable that way. So here, if we plug in 2 for x2 here, we just get 6 here. I subtract 6 from both sides, I get 2. 2x1 is equal to 2, so now we know x1 is also equal to 1. So if I did that too quickly, just pause the video, try to see how I got x1 is equal to 1. Once we know x2 is equal to 2 here. And if you're confused why x2 is equal to 2, then definitely ask me a question. So start out with two equations. They're linear equations, meaning that there's just some coefficient times the first variable to the power of 1. There's no non-linearity in the variables themselves. And there's just some real number times the first variable plus some real number times the second variable is equal to some real number. And in this case, we have two of these type of equations, two variables, and we solved and said that there was actually only one unique solution here. x1 had to be equal to 1, and x2 had to be equal to 2, and there's no other solution in this case. But more generally, there could be either no solutions, exactly one solution, or a space of solutions, which will either be one-dimensional, which would be like a line, or you could have a two-dimensional space of solutions, like a plane, three-dimensional space, like some sort of, cubical space, and they can also be embedded in higher spaces as well. So you could have like a three-dimensional solution that's existing in some 5 or 6 or 8-dimensional space. Right, but in this case, we have a two-dimensional space, and our set of solutions is zero-dimensional, and we just have a single point, which is the point 1, 2. That's the only solution. Right, and just to repeat myself once more, this is sort of like your motivation. We haven't talked about vector spaces yet, but you can already sort of see that they're creeping in here, because this x1, x2 list of variables, you could see it as a vector in R2. It's like a point in R2 in the plane. You just need two coordinates to describe its position. And in general, yeah, so actually what we'll write this down in a second, but there's another way to write down this system of equations in sort of a more linear algebra type way. So this is motivation, but we're not really going to solve problems this way in general. So let's write down a different form of the equation, which is called the matrix form, and that's kind of the more mathematically useful form of the system of equations. So we're going to look at the same system, but we're going to convert it into like a matrix form. So any questions at all? Any questions at all? Doesn't have to be about linear algebra. Okay, so let's look at the matrix form of the same equation. And I actually kind of want to skip the literal definition of matrix multiplication. I think you can probably pause the video, or if you're watching later, or just go right now and look up the definition of matrix multiplication. It's kind of tedious, the definition. Also, if you look up dot product, that might make it a little easier because you can kind of view matrix multiplication as like a bunch of dot products, and that might make it simpler to remember. But here for this 2 by 2 matrix, it'll be pretty simple. So I'll do out the multiplication for you, and hopefully you can look up the more general result and figure out what's going on. But here, so before, let me write in the corner what our equation was. So we had 2x1 plus 3x2 is equal to 8. And we had 10x1 plus 1x2 is equal to 12. And so the matrix form, you're basically going to just take the coefficients the way they look in this form, but you do have to make sure that the variables are all in the same order and that they're not out of order. So like the first variable is always first and the second variable is second, etc. But if you make sure all that stuff is satisfied, then you can just literally read the coefficients off here. So it's going to be 2, 3, 10, 1. And this we'll call the matrix of the system of equations, or it could be the matrix of some sort of linear map, which we'll talk about in a second. But and now this system of linear equations can be sort of reworded. So what we can say is that we can really reword this in terms of vectors and a linear map given by multiplication by this matrix. And what we're really looking for is a solution where we have a vector b, which is 8, 12. Right? And when I write a vector, it's just a list of numbers, but a lot of the times I'll list the numbers vertically. So this is the first number, 8. This is the second number, 12. This is a two-dimensional vector. This is a 2 by 2 matrix. And this equation is really asking, is there some vector x, which has two numbers, x1, x2, such that when I do the matrix multiplication, A times x, the x vector, is there a solution for the vector x such that A times x equals b? So this is the matrix form of the equation. It involves matrix multiplication, which represents a linear map, essentially. We'll go through the theory of this a little bit later, or a little bit, a couple lessons from now. But yeah, if you look at the definition of matrix multiplication and you look at what this equation is saying, you'll see it is simultaneously saying that the first variable has an equation that it needs to satisfy, and the second variable has to satisfy another equation that equals the second term in b. here, which is 12. So really this single equation is, it's really like a vector equation, right? We're saying the vector on the left is equal to the vector on the right, and vectors are only equal if each entry is equal. And that's where we get this system of equations. So we're saying that not only does the first value have to be satisfied, it has to be equal to the first value of b, but the second value has to be equal to the second value of b. And so this is really a vector equation. It's saying that the vectors have to be equal, and therefore vectors are equal if and only if the entries are equal. So every element in the list has to be equal, and that just gives us this system of equations. Okay, and a more like theoretical way of looking at it is we have a linear map given by multiplication by a. B is some vector in R2. A is representing a linear map from R2 to R2. And when we ask, does this equation have any solutions, or this set of equations, does it have any simultaneous solutions? Really what we're asking is B in the image of this linear map? Because this linear map applies to x and it's equal to b, and we're asking the question, are there any vectors x such that when I multiply by the matrix A, I get the vector b? So I'm using some sort of like higher language that we haven't talked about yet, but this will be, this will all become common language that you use if you're taking this class or you're studying this subject. So let's just get it out of the way real quick, and we'll use the language here to point out that in linear algebra language, we're really asking, does the linear map given by multiplication by a, does it hit this vector in the image? So I'll write it here in like parentheses because we're not being super exact here, but we're just asking the question, is the vector b in the image of a, of the map A, or the image of the map given by multiplication by a, really, but sometimes we'll just write image of a. Or some other terminology that's common in linear algebra is you'll ask, is b in the span of the column vectors of a? So that's another way of asking the same question, right? So the column vectors of a would be this vector and this vector. And to ask, is b in the span of these vectors, we're just asking, can we write b as a linear combination of these two vectors? And that's essentially equivalent to the original solving of the simultaneous equation, because this basically is some linear combination. This is the multiplication by a. We're saying, is there some multiplication by a by some vector that gives us this b vector? If there is, we want to know what is x. So we're trying to solve what is this vector x. We know what b is already. We're usually given b. We really want to know what is the vector x that when I multiply by this matrix A, I end up with this vector b, that it's in the image. Okay, and then Axler kind of develops this notion of, what is a vector space abstractly? What are the properties of it? What are some things we can say hold for sure in any vector space, whether it's finite dimensional, infinite dimensional, just no matter what. But really the motivation is these linear equations, matrices, and Rn, Cn, finite dimensional vector spaces, and solving these equations. Okay. So let me write just one quick note. I already said it, but let me just write it down. Or yeah, actually, let's use the matrix A that I just erased, and we'll show that multiplication by A is a linear map. So we'll state again, we'll state for the first time what is a linear map. Well, I didn't even define vector space, I guess, but let's just stick to this multiplication. All right, so there's there's some map LA, which will be multiplication by the matrix A. It's going to be a map from R2 to R2. So I'm going to feed it two-dimensional real numbers. I'm going to feed it two real numbers, essentially. And it's going to map it to two other real numbers, and this map is going to be linear in a sense, which we'll write down in a bit. And the map is I just take x1, x2, and I send it to multiplication by A, which in particular, if A is the matrix that we had before, 2, 3, 10, 1, then this is, so multiplication by this matrix with this vector is just the vector 2x1 plus 3x2 and 10x1 plus 1x2. So this is a two-dimensional vector, and you can see that each entry is linear in the two variables x1 and x2. And you know, I haven't really defined what linear is yet, but just take my word for it that it's linear, so it has to satisfy a certain linearity property, and we'll show that multiplication by a matrix always does satisfy that. But so here's our map, and so now you'll see that rewording the problem, what we had before, we had this vector b, which was in the image, and we wanted to know if this was ever equal to the first entry of b, and if the second thing was ever equal to the second entry of b. And that's just really asking, you know, when b is in, when I pull some random b from this space, is there some x that maps to it under this multiplication? If there is something that maps to it, then that's the solution that we wanted to get. That's the solution of the simultaneous linear equation. It satisfies these two things at the same time, that 2x1 plus 3x2 is equal to that first entry of b, and 10x1 plus 1x2 is equal to the second entry. Okay. And in general, this is how this matrix multiplication works. You're really taking a dot product here, so it's yeah, I don't think we have time right now, but yeah, look up matrix multiplication if this is confusing. But this is what happens when you take x1, x2, and you multiply by a matrix A, or this matrix A. In particular, you get this vector. So this is a vector. This is only two entries. This is the first entry, and this is the second entry. Okay, so really what we want to know is, with this linear map, what is the set of solutions and how big is the space? So what is the x vector that satisfies this, or satisfies ax equal to b, like before? And I ran out of room, but so we want to know what is the x that satisfies this equation, but not only what is one particular x, but what is the size of the space of all solutions? Is there only one answer, and is it, which would make it zero-dimensional? Or is there a whole line of solutions where if I pick any entry on the line, it's also a solution? Or maybe I have a two-dimensional plane of solutions where if I pick any vector on that entire plane, it's also a solution. So essentially, you have these linear equations, and the set of solutions is some linear subspace, and you want to know how big is that subspace. Is there only one solution? Is there a line of solutions? Is there a whole two or three or larger space dimensional space of solutions, which is always possible. But your set of solutions is going to depend on the dimensions of the input and the output. So here we have R2 and R2, and if the dimensions are the same and this map is what we'll call invertible, then there's always going to be one unique solution, which is the case in this example. There's that LA is actually an invertible linear map. There is an inverse to this matrix, and if we multiplied by the inverse of the matrix, we would be able to undo this process and basically go back to the solution. But not every linear map is invertible, so this attempt to go backwards doesn't always work, and it can't always work if there's more than one solution, right? You can only go backwards using the inverse if there's only exactly one solution if the dimensions are the same. So there's a lot of things you need to be careful with here, but a lot of it depends on what's the dimension of the vector space on the input, what's the dimension of the vector space on the output, and what's the dimension of the kernel space, which we'll talk about eventually. But the kernel is, everything in the domain that maps to the zero vector of the codomain. So all of these things work into the size of the set of solutions. How big is the dimension of the domain? How big is the dimension of the codomain? And how big is the dimension of the kernel of the linear map? And there's this rank nullity theorem that says if you add up the dimensions of the image of the map and the kernel of the map, that they have to add up to the dimension of the domain. So that's an important theorem, which we'll get to eventually, but it shows you that there's a lot of rigidity in the dimensions of these, particular spaces, and you're restricted by the size of the kernel of the linear map based on that stuff. Okay, so our main question is, given this matrix equation, some matrix times a vector is equal to some vector that we know. Can we go backwards and figure out what x is? And if so, if there is some x that satisfies it, is there another x? And if there's two x's, there has to be at least infinitely many x's. And if there's infinitely many, what's the size of, or the dimension of that space of solutions? It could be one-dimensional, two-dimensional, etc. Okay, and then I just want to briefly go through the definition of a vector space, and then we'll basically be done. Maybe I'll talk about linear maps next time, because I kind of already went over it a little bit briefly here, but we'll write down the definition next time. Let's just write down what is an abstract vector space. We said basically they're all either n-dimensional real numbers or n-dimensional complex numbers. But abstractly, if we didn't know that those were the only cases, what would we call a vector space generally? So that's this definition. It's kind of long, but I would say it's intuitive for a mathematician, but maybe it's a little unintuitive for someone seeing it for the first time. All right, so this is on page 12 of the book I just showed you, the Axler book. So page 12 in Axler, and this is his definition 1.20. So he says a vector space is basically just a set V. So you have some set of elements, which we'll call vectors. Well, it's not just a set, it's actually an abelian group under addition. So it's a set, which is also a group under addition. And it actually needs to be a commutative group. So A plus B has to be the same as B plus A for any A and B. And that's usually what we call an addition, is a commutative group product. So a vector space is a commutative group under addition, and there's also a scalar multiplication component. So if I take something from a field, and we'll usually say there's a vector space over a field F. So a vector space over F it's an abelian group under addition, and we have scalar multiplication by things from the field. So if I take a vector and I can multiply any vector by some real number or anything from the field, and I should get some other vector, and that should be invertible in the sense that if I multiply by the inverse of that element in the field, that I should go back to the original vector. But we'll get into that in a second. So basically a vector space, it's a group with addition, and then it also has a scalar multiplication. Such that, and I'll write ... and we'll write down all the properties here. But I do want to emphasize here that we have two binary operations basically. We have addition, which is the plus sign. All of our vectors can be added to each other, and this addition is commutative, so it doesn't matter the order in which I do the addition. And now we have a second binary operation. Well, it's not really a binary operation, but it's a map from F times the vector space V. Vector space V. So if I pick a vector from V and I pick a number from the field, then there should be some way of multiplying the element of the field times the vector, and I should get a new vector. So there's two operations going on here. There's plus and there's scalar multiplication, and these two have to interplay with each other and satisfy a number of axioms, and then we say V is a vector space over the field F if these things I'm about to write are satisfied. So two operations, addition, which is within the vector space itself, and then we have scalar multiplication. When I take a scalar from the field and multiply by a vector, I get a new vector. And we say that the vector was scaled by the scalar in the field. Okay, so the two operations have to satisfy all of these properties. So one is that u plus v has to be equal to v plus u for all vectors. So this is our set theory symbol that says for all. So for all vectors u, v, and v. And this is just saying the commutativity property is satisfied under addition, so that basically what I said before, that the addition needs to be commutative, that doesn't matter whether I do the addition in one order or the other, I get the same thing. So commutative under addition. Associative under addition, this is just more group theory axioms that we already talked about in the first videos. And this needs to be true for all V, U, and W in V. Right, so this is the associativity property, right? If I do the addition on the first two elements and then I add the third element to the result of the addition, it should be the same thing as if I took the first element and added on the left or the right, since it's abelian, doesn't matter. But if I group them in a different order, so I group V and W together first, and then I add U to it at the beginning, should be the same thing. So the grouping doesn't matter. We have associative addition. Yeah. Oh wait, also associative under the scalar multiplication. So if I take A and I multiply by B scaling a vector V, it should be the same thing as if I multiply A and B in the field first and then I scale by the product. And this, again, this should be true for all A and B in the field. And obviously for every vector V, I'm not going to write for all V, but it's still here for all V. So for any vector, the associativity of the scalar multiplication is also satisfied. 3 is that there's a zero vector, so there exists a vector 0. Sometimes I'll write 0 with a little arrow above it, so there's some vector 0 in V such that when I add it, I just get the same thing back. So 0 plus V is equal to V plus 0, which is equal to V for all V. It's just the element that when I add it to a vector, I get the same vector back. It's like the additive identity. 4 says that there's an inverse, so we're still working on group theory axioms, except for this one right here. But this one says that for all V in the vector space, there exists a W in the vector space, and when I add these together, I get 0. Okay, so just saying that our vectors have additive inverses. All right, so basically everything here is the group theory axioms, with the addition that the first one says that it's an abelian group, that it's commutative under addition. Except for this one right here, like I was saying, this is something to do with the field. That's not just to do with the vector addition operation itself. So yeah, first four mainly talk about the vector being an abelian group, except for this one. And now into 5, we're going to be talking about how the field acts on the vector space. So these are the first 4. If you need to write them down, I would just pause right here. And then we have an additional 5 and 6 that the field needs to satisfy. Okay, and then 5 says that if I take the number 1 from the field, so there always needs to be some number in your field that acts as the identity under multiplication. If I take that element 1 in the field and I scale a vector by 1, then it shouldn't do anything to the vector. So I scale a vector by 1, I just get v back. That should be true for all v in the vector space. And finally, one of the most important ones is the interplay between the two algebraic operations. And this is called the distributive property, which I'm sure you've seen before. So this says if I scale a sum of two vectors, u plus v, should be the same thing as if I scale the vectors individually and then add them together. Or in other words, we're saying that multiplication on the left by a scalar is basically a linear map. That a times u plus v is a times u plus a times v. So that's literally saying that multiplication on the left acts linearly on the abelian group of vectors. And also, we have another property, which is that if I add vectors in the field, they also distribute over the vector space. So multiplication on the left, multiplication on the right by a vector is actually linear in the field as well. So it's linear in the operation of the addition on the vector space, but the addition on the field is also linear. So a plus b acting on some vector is just a acting on the vector plus b acting on the vector. Right, so we have some sort of interplay between the two operations. We have vector addition, which is abelian and has to satisfy all of the axioms 1 through 4 that I just erased before. And then we have the scalar multiplication, where I can take a scalar and I can multiply it by a vector, and I scale the vector. In this case, if I scale by 1, I don't change the vector. But if I scale by some other scalar, maybe by 2, right, then I could undo the scalar multiplication by then multiplying by 1/2 later. And we have the associativity of the scaling, which was, I think, was 2 that I erased before. So the second part of number 2 I erased before. So that says the scalar multiplication itself is associative. So I can multiply by 2, then I can multiply by 1/2, and I should get back the vector I originally started with, because the associativity and the fact that 1 times the vector is itself, and 1/2 times 2 is 1. So. Wire plumber? Okay. Yeah, it's a Jewish concept. Okay. I'm just going to ban this guy. And you're banned. Okay. Right. So if you have a vector space, which is just an abelian group, you have some field which acts as scalars, and it satisfies these 6 axioms, then we say that we have a vector space over a field F. And the study of linear algebra is going to be a study of linear maps between vector spaces, essentially. So you have a vector space in the domain, you have a vector space in the codomain, you have some map that respects basically the structure that we just outlined, and that is what a linear map is. And linear algebra is basically the study of these linear maps and what is the size of the dimension of solutions, and various things about the linear map, mainly the image, the kernel of the map, etc. Who is Yakub? All right, so yeah, let me just write down what I just said, but essentially, so linear algebra is the study of linear maps between vector spaces. I'll just write BS here. All right, so you have two sets that satisfy these axioms, 1 through 6. You have a map, which we'll discuss next time, which preserves the linearity in some sense. So it sends, actually you can kind of see the preservance of linearity here in this equation. A times some sum is equal to A times the first thing plus A times the second thing. When we have linearity between vector spaces, that's a function between the spaces that preserves this linear structure in some sense, so that you can say that the image of the map is also a vector space, and you get some nice properties like the kernel of the map in the domain is also a subspace, and they have some uniquely defined dimension, which is an integer usually, unless you're dealing with infinite dimensional spaces. So yeah, that's kind of what we'll be getting into here. We'll talk more about what is a vector space. We just wrote down the definition, right? But we'll talk about a little more properties of vector spaces, properties of the zero, of inverses. You can show uniqueness of certain things like the dimension and other things. Yeah, so I think that's it for now. I got a comment there, but I'm not really sure what it means. Yeah, you banned. Yakub taught me this a while back. I'm not sure what that means, but if you want to ask another question, I'll still be here. I'm going to end the video here.